Hello everyone, hope all of you guys are doing well. And here's our chapter 18 lecture slides. Okay, so what are we gonna do in this chapter? Alright, so we're gonna be learning about acid base equilibria in this chapter. Okay, so let's see what we have in store for us for this chapter. We're gonna learn the behavior of acids and bases in water. Okay, and autoionization of water and the pH scale, proton transfer and the Bronsted-Lowry acid-base definition, solving problems involving weak acid equilibria, weak bases and their relation to weak acids, molecular properties and acid strength, acid-base properties of salt solutions, and generalizing the Bronsted-Lowry concept, which is called the leveling effect, and electron pair donation and the Lewis acid-base definition. So basically we're going to learn what is an acid and what is a base, and there are three acid-base concepts that we're going to learn. The first one is called Arrhenius acid-base theory, the second one Bronsted-Lowry, and then the third one Lewis acid-base definition. Okay, now let's learn all of that. Now you know acids and bases we use in our day-to-day life, and I'm sure you guys also must have used some of these acids and bases, but they can be identified in commercial names. Now you will know what is the active ingredient in terms of acids and bases in these commercially available ingredients. Okay, commercially available products. So let's say acids, acetic acid. Acetic acid we find in, where do we find acetic acid? In vinegar, right? So you use vinegar at home, and it's very popular among us that apple cider vinegar has a lot of health benefits. So acetic acid is the acid that you find in vinegar, and it is a flavoring and also a preservative. And citric acid, another acid, citric acid, again it's a flavoring. Ascorbic acid, ascorbic acid we find in vitamin C. Vitamin C is basically ascorbic acid. You find it in nutritional supplements too. And also you find in the fruits, oranges, ascorbic acid, right? And then the aluminum salt, sodium aluminum sulfate, 12 water molecules. You find it in baking powder with sodium hydrogen carbonate. So those are some of the acids. And some bases are sodium hydroxide. Sodium hydroxide, oven and drain cleaners, you find that. And then ammonia again, the formula NH3, it's a household cleaner. And sodium carbonate, Na2CO3, which is a water softener, grease remover. And sodium hydrogen carbonate or sodium bicarbonate, here you find in baking soda, a fire extinguisher, rising agent in cake mixtures, that comes in the name baking soda, and also it's a mild antacid. And sodium phosphate, which is again a cleaner for surfaces before painting or wallpapering. Okay, so these are some of the acids and the bases that we use in our day-to-day activities. Now the first definition, Arrhenius acid-base definition, this is the earliest definition. Yes, this is the earliest acid-base definition, which classifies these substances in terms of their behavior in water. Okay, an acid is a substance with hydrogen in its formula that dissociates to yield H3O+. So basically acid is something that you have hydrogen in it. And base is a substance with OH in its formula that dissociates to yield OH-. So in the earliest definition, Arrhenius acid-base definition, acid is when you have hydrogen in its formula and that dissociate to give you H3O+, and base is when you have hydroxide in the formula. So basically, when acid react with a base, they undergo neutralization. Neutralization is it forms a water molecule. Water is very neutral. If you take the pH of the water, it would be 7. So basically H plus coming from the acid, hydroxide coming from the base together form a water molecule. That called a neutralization. Normally acid-base reactions are called neutralization reaction because it forms a water molecule and a salt. Okay, and this is delta H. Enthalpy for the reaction is negative 55.9 kilojoules. Now, is this an exothermic reaction or an endothermic reaction? If it is negative, it's going to be exothermic reaction. So that is why you would see, if you do acid-base reaction, if you touch the flask that we do the reaction, it will start, you will feel warmness, meaning it generate heat. It's exothermic reaction. Okay, it releases heat to the environment. Now we have strong acids and strong bases and weak acids and weak bases. Let's look at some strong and weak acids. How do you find out whether we have a strong acid or a weak acid? Now, a strong acid normally dissociates completely into ions in water. Now, let's say this is our strong acid, HA. It could be gas or liquid. H is the hydrogen ion, A could be the counter ion. If it is HCl, A would be chlorine. If it is HBr, A would be bromine. Like that, hydrobromic acid, hydrochloric acid. When you put it into water, it's going to dissociate to give you hydronium ion, H3O plus and A minus. Basically, this hydrogen combined with water to form hydronium ion H3O plus and A minus. So the A counter ion would be lost and it would dissociate into A minus. Okay. Now a dilute solution of a strong acid, meaning you have acid, you add water, then it becomes diluted, contains no HA molecules. What does that mean? So when you add water, you will not find this intact molecule of HA, because strong acid means it completely dissociates into its ions, hydronium ion and A minus. Okay, that's why strong acid contains no HA molecules. Whereas a weak acid, let's say this is a weak acid, you put it into water. Now here you can see the reversible arrows. Here only one-sided, meaning a strong acid completely dissociates into ions, whereas a weak acid, it is a forward reaction and backward reaction, both. Okay, so the products are going to be the same, hydronium ion and A minus, but the percentage of dissociation would be very less because it's a weak acid. Okay, so in a dilute solution of a weak acid, most HA molecules are undissociated. If it is strong, it will completely give to ions, but if it is a weak acid, it would mostly HA would stay as undissociated acid. Okay, so if you write, now this is going to be your reaction, this is your reactants and this is your product. And if you write the equilibrium constant Kc, remember we learned about the Kc in the previous lecture. So your products, hydronium ions A minus over the reactants HA and water, which has a very small value, meaning the forward reaction is very less. You only have less amount of hydronium ions and A minus dissociated. Most of the HA molecules are undissociated. Okay, now you can see this in this diagram here. Okay, extent of dissociation for strong acids. Now let's say this is our HA before you put it into water, right? There are two number of molecules, so you put it into water. Now this is the green in color, HA. After they dissociate, do you see any green here? Nothing, no HA molecules. What do you have? H3O plus represent the blue and A minus represent yellow. Okay, it will completely dissociate into hydronium ions and A minus ions. Okay, so these are A minus, all of these, and these are hydronium ions. Okay, and so this is the hydronium H3O plus. This is oxygen red, and these little blue ones are going to be your hydrogens. There are 3 hydrogens, H3, 1, 2, 3, and this is oxygen. So the strong acid Ha plus water, hydronium and A minus, there are no HA molecules in the solution. Completely dissociated. Okay, because it's a strong acid. Now let's look at if you have a weak acid, what's going to happen. Extent of dissociation for weak acid. Now this is your weak acid, green in color. You put it into water, that also dissociate to give you hydronium and A minus. But what about the HA molecules? So most of the HA molecules are undissociated. It only dissociate less amount, hydronium ions and A minus right here. Okay, and these are HA molecules. HA, HA, HA. You can see lots of HA molecules are undissociated. And these ones, the blue ones over here, blue and kind of gray ones, they are your water molecules. So you have plenty of water in the medium, that water. Okay, so most HA molecules are undissociated. So the dissociation of the molecule or the acid molecule depend on the acid strength. If it is a strong acid, it would dissociate completely, and if it is a weak acid, the acid would dissociate very less amount. Most of the acid would stay intact because it's a weak acid. Okay. Now the acid dissociation constant Ka. Remember in the previous slide we saw that for a weak acid we can write the equilibrium constant, which is the concentration of products over the concentration of reactants. Hydronium ions times A minus over HA and water. HA is the weak acid concentration, water is the here water, right? Now normally if you have an acid in water, water molecules are the number of water molecules are huge compared to the HA molecules. Compared to the acid, we find lots of water molecules. So since the water concentration is a lot and which is going to be a constant, so we can take the Kc and water into one side. So you take this Kc water to the same side as Kc. So Kc times water. Now since water is a huge amount and it is abundant and it is a constant, so Kc times the concentration of water together gives us a new constant. We call it as a acid dissociation constant Ka. So the acid dissociation constant Ka is basically hydronium ion concentration times the conjugate base over HA concentration. Okay. The value of Ka is an indication of the acid strength. Now if it is a stronger acid, we will have a higher hydronium ion concentration. Remember, if it is a weak acid, this will dissociate completely excuse me, and hydronium ion would be concentration would be more, so this term would be more. So as a result, what happened to the Ka would be larger, right? So this is the expression for the Ka. If it is a stronger acid, you have a lot of hydronium ion in the medium. If this term increases, so the Ka would be higher, so the larger Ka. Now let's say you have a weaker acid. So weaker acid means dissociation is less, so the hydronium ion concentration would be less, so the Ka would be smaller. Lower percent dissociation of HA, as a result smaller Ka. Okay. So if you see Ka values, meaning the acid dissociation constant values, the larger Ka value meaning it is a stronger acid. Smaller Ka value meaning it is a weaker acid. Okay, comparing the weak acids. Okay, So in weak acids also we can see what is a stronger weak acid, what is a weaker weak acid, like that. Now here's some K values for some monoprotic acids. Monoprotic means, what is monoprotic? Protic means protons. Protons means hydrogens, right? So mono means one. So these are some of the acid which has only one hydrogen. One, you see, one hydrogen. So these red ones are the ionizable hydrogens that is responsible for the acidity of the molecule. You can see there are some other hydrogens, but they are not removing, or they are not involved in the acid strength. Okay. Now this is chlorous acid, HClO2. So this is just one hydrogen. This is the Lewis structure, and Ka given to us 1.1 into 10 to the negative 2. And then the nitrous acid, HONO, 7.1 into 10 to the negative 4. And hydrofluoric acid, HF, formic acid, so this is the hydrogen that is connected to the oxygen is what responsible for the acidity, not this hydrogen. Okay. And acetic acid again, this is the hydrogen. Propanoic acid and hypochlorous acid, hydrocyanic acid. Hydrocyanic acid, which is this hydrogen, only one hydrogen, that's making it acid. Now if you look at the Ka values, negative 2, negative 4, negative 4, negative 4, 5, negative 8, negative 10. So this one is a small amount compared to this number, right? So meaning this is Ka is a smaller number, K is a higher number. So then the acid strength you can see increases along this way. So all of these are weak acids. Okay, so for weak acids also we can see out of the weak acid which one is a stronger weak acid. So chlorous acid is a strong weak acid compared to nitrous acid, and so this is how the order for this particular group of acids. Okay, so the acid dissociation constant tells us how strong is a weak acid. Okay, classifying the relative strengths of acids. Now here's another way that we can look at by glancing an acid whether they are going to be strong acids or a weak acid. Strong acids include the hydrohalic acids. Halic acids. So halic acids are coming from halogens. Halogens are the elements you find in the periodic table group 7. Okay, hydrohalic acid meaning it has a hydrogen group and a halogen. So out of the halogens, the first three halogens are going, the very first halogen is the fluorine. Out of you don't take the fluorine, but after fluorine you have chlorine, bromine, iodine. So they are strong acids, but HF is a weak acid, the first halogen. Okay, so strong acids include HCl, HBr and HI. And then you will also find some oxo acids. Oxo acids meaning when you have oxygen in the acid. Now here you don't have oxygen, so you don't call these as oxo acids. So they are hydrohalic acids. Oxo acids in which the number of oxygen atoms. Now in our acids you can have oxygen and hydrogen. So number of oxygen atoms exceeds the number of ionizable protons by 2 or more. They are considered strong acids. Now here you have one ionizable hydrogen. Okay, and then the number of oxygen atoms 3. So in which the number of oxygen atoms 3 exceeds the number of ionizable proton, in this case 1, by 2 or more, they are considered strong acid. So there are 3 oxygens compared to 1, it's a strong acid. And if you take H2SO4, sulfuric acid. So sulfuric acid has 2 hydrogens and 4 oxygens. Number of oxygen atoms exceeds the number of ionizable protons by 2 or more, right? So that is also considered a strong acid, sulfuric acid, nitric acid. And here HClO4, again there are 4 oxygen compared to 1 hydrogen. Okay, and then the weak acids, they include the hydrohalic acid HF, the very first halogen with the hydrogen, that's a weak acid. And then acids in which hydrogen is not bonded to oxygen or to a halogen. Let's say you have an acid, we call it as acid, but hydrogen is not bonded to oxygen or to a halogen. So they are also called weak acid. For example, HCN, hydrocyanic acid, hydrogen is bonded to carbon. And then oxoacids, in which the number of oxygen atoms equal or exceeds the number of ionizable protons by 1. Here it is by 2 or more, by 1. 1 hydrogen, 1 oxygen, 1 hydrogen, 2 oxygen. Okay, so they are weak acids. And then carboxylic acids, which have the general formula. You have an alkyl group which is called R group, and the general formula for carboxylic acid, you will see carbon with 2 oxygens and hydrogen. So this group, when you find this group, we call it as a carboxylic acid group. For example, this one, CH3, carbon, oxygen, 2 oxygens and hydrogen. And another one, C6H5, carbon, 2 oxygens and hydrogen. So this carbon, 2 oxygen and hydrogen, this is an indication of a carboxylic acid. Okay, so they are all weak acids. Okay, so this is the, remember I told you that hydrogen, 2 oxygens and carbon. So this is how they are attached, the Lewis structure. Carbon will have a double bonded oxygen with a pi bond, and then you have another oxygen attached to hydrogen. So this group is the carboxylic acid group part. Okay, they all are weak acids. So these are all weak acids. Now let's look at some bases. So we learned about the acids, and now let's look at some relative strengths of bases. So bases also, we have strong bases and weak bases. So now what are strong bases? So water soluble compounds containing O2 minus or hydroxide ions, they are considered strong bases. Hydroxide, for example, sodium hydroxide, potassium hydroxide, those are all calcium hydroxide, strong bases. The cations are usually those of the most active metals. Now in a base you need to have a cation, like when you say sodium hydroxide, right? So not all the hydroxides are going to be strong bases, but the cations coming from most active metals. Most active metals are group 1A metals like sodium, lithium, potassium, rubidium, cesium. Them and their oxides and hydroxides, they are strong bases. And also group 2 metals, metal oxides or metal hydroxides in the group 2, calcium, strontium, barium. Them, they are hydroxides and their oxides, they are also strong bases. Okay. Okay. Okay, so those are the strong bases. Strong bases of hydroxides and oxides of group 1A, metal, lithium, sodium, potassium, rubidium, cesium, or group 2A metal, calcium, strontium, barium, and their oxides and hydroxides. Okay, and then the weak bases, they include ammonia. Ammonia is a weak base. And then any amine. Amine means when this ammonia, nitrogen with 3 hydrogens, and these hydrogens can be replaced with any other groups like this. So we commonly give them the R representing alkyl group, which normally we use in organic chemistry, but R could be a different group, different carbon group. Okay, so which have the general formula, it coming from ammonia It also has the nitrogen. Instead of 3 hydrogens, it can have 2 hydrogens and 1 R, or 1 hydrogen and 2 R groups, or 3 R groups. So they are derivatives of ammonia, and they are all also considered weak bases. Okay. The common structural feature is it has a nitrogen atom with a lone electron pair. You see here there is a lone pair. When you have lone pair, that can be considered as a weak base. Now, let's classify each of the following compounds as a strong acid, weak acid, strong base, or weak base. Now, what do you think about the first one? So, our first one is KOH. What is KOH? Potassium hydroxide. What is it, acid or a base? So how do you find? When you have OH, hydroxide, which is a base, and the base is combined with an active metal from the group 1 KOH. So then it would be a strong base. This one, remember what is this group going to be? You have carbon, 2 oxygens and hydrogen, and I showed you this is the carboxylic functional group. So that carboxylic functional group is belong to a weak acid. So it is a weak acid, right? And then what about the next one? So though in the B you have there are 6 hydrogen and you have another hydrogen, they are all connected to carbon. So this hydrogen connected to oxygen is the only ionizable hydrogen that will make you a weak acid. And in this one you have H2SeO4. There are 2 hydrogens and there are 4 oxygens. And then this one, this is an oxo acid. Remember, there are 2 hydrogens and along with oxygen. So this is an oxo acid in which the number of atoms, number of oxygen atoms exceed the number of ionizable protons by 2. There are 4 oxygen atoms and 2 hydrogen atoms. So number of oxygen atoms exceed the number of ionizable protons by 2. So that will make it a strong acid. What about D? So D here you can find there is a nitrogen in it. Remember, ammonia is a weak base, and any derivatives of ammonia where ammonia is NH3. So you have 2 hydrogens and the other group is alkyl group, which is the R group, making it a weak base. Okay. You can also see the answer choices here. It's a weak base. Now, what is autoionization of water? Normally, when you have 2 water molecules, we have plenty of water, right? When you have water, so what happens is oxygen. So this is your oxygen atom. There are 2 hydrogens and it has lone pairs, 2 lone pairs. Now, how many electrons do we need to make a bond? We need 2 electrons, right? So these lone pairs has 2 electrons each. So one of these lone pairs can go and extend its 2 lone electrons to form a bond with another hydrogen of a neighboring water molecule. So they make a connection. So give these 2 electrons and make a bond with that guy. Okay, and then the bond between this hydrogen and carbon, not the carbon, oxygen will break off, right? So then this molecule will end up having 1, 2 and 3 hydrogens, and with only 1 lone pair, because one of the lone pairs used to form a bond. So now since it has 3 hydrogens, 1, 2, 3, this would become hydronium ion, oxygen with 3 hydrogens, H3O, and this would be a positively charged because that is the formal charge when oxygen has 3 hydrogens. Now what about the other water molecule? It has lone pairs, 2 lone pairs. Now since this hydrogen and oxygen bond breaks and there are 2 electrons in this bond, and this hydrogen doesn't need that 2 electrons because it's getting from this lone pair the 2 electrons in this bond given to this oxygen. So as a result, oxygen will end up having 3 lone pairs. 2 electrons from this bond and the 2 that it already had. So it will end up having 1 oxygen and only 1 hydrogen from H2O, and it has 1, 2, 3 lone pairs. And if you look at the formal charge, calculate the formal charge, you will see this OH will carry a -1 formal charge. So this would be H3O plus and this would be OH minus. Okay, so water dissociates very slightly into ions in an equilibrium process known as autoionization or self-ionization. So basically, when you have two liquid water molecules, you have one hydronium ion and a one hydroxide ion, and that is called autoionization of water or self-ionization. Okay. Okay, so let's stop here and then we can continue the rest in the next